our long-run relationship among the variables. So this is for this speed of adjustment is actually in the short run. See, when you are reporting the result, you need to add it to the short run result, because the shocks, the disturbances will happen in the long run. We expect that in the long run, the variables will move together. So when you are reporting your results, you need to add this speed of adjustment to your long run result. You bring it at the last end. Okay, now let's come here. So if you look at, let's first determine whether there's a long run relationship before I come to explain the result. Because if there's no long run relationship, then it means that we only need to rely on the short run result. We cannot make any meaningful analysis of the long run result. So let's look at our result and see if there's a long run relationship. So what we use in determining the long run relationship here is that we use the F statistics test. So this is our bound test. So our bound test, the null hypothesis here is that there's no co-integration among our variables. That's a null hypothesis. So we're going to use the F statistics in determining whether there's a long run relationship among our variables. So what to do here is that we have the result here, we have the upper bound and lower bound. We have upper bound and lower bound. Somebody has raised their hand. Okay, actually, I wanted to go through the result before. Okay, let me hear you out, Cynthia. Okay, Cynthia, you can ask your question. What's your question here, Cynthia?
Unmute. Okay, good afternoon.
Good afternoon.
Please, I need you to go back to where you did the 2-2-3-3-2-2 to get us to this regression table.
Okay, okay. I'll do that for you. Okay, all right. So let me go back. If you're watching, so after we declare our data set, the next thing we're supposed to do actually was to determine the stationarity of our variables. We have to make sure that we know the integration order of our result. But here, because I don't want us to waste a lot of time on that, I presume that our variables are stationary at the levels or at the first difference. So that's what, because the ideal is it's not applicable when any of the variable is integrated of order 2. So here we are presuming that our variable is integrated of order 1 or 2. Then after that, we look at we determine the maximum lags or the optimal lags of our variables. So we type VASOC then for each variable. So you type VASOC. Here we have the carbon emission. That's our dependent variable. Then we look at we determine the optimal lag of it. So the result, you notice that the optimal lag for carbon emission is 2. So we do that for individual. We just determine the optimal lag for each variable in our data set. That's what I did. Then after we've been able to determine the optimal lag for each variable, we go ahead to estimate our ARDM model. So let me get to where we run the ARDM. So after that, after we determine the optimal lag, if you've not installed the ARDM model, then you have to install ARDM model by using this code, this command here, in order for you to have ARDM in your STATA. Then after that, we move on to specify our ARDM model and run it. That's what we did. So I write the ARDM, then after that, our dependent variable, then the regresses. Then we bring comma, then after comma, we have the lags. So what we have to do here, is that we write the optimal lags of the variables that we're using. That's what I did. if you look at where I got the result, you notice that where I got the result, I have to omit I omitted life expectancy from our variable because it's the system the STATA actually indicated that variable has a problem of multicollinearity, so it was dropped. So I have to run the regression. So if you look at our current result now, we don't have life expectancy because it has a problem of multicollinearity. So this is a command I used to run it. I will later use a different approach so that will be easier. I hope, Cynthia, you understand that. Now let's move on to determine whether there's a long-run relationship among our variables before we come back to our results and analyzing them. So let's look at the bound test result. So with the bound test, we will use the F statistics to determine whether there's a long-run relationship. So what you need to understand here is that we have upper and lower bound. So the result that you see under the I0, those are the lower bound. Then the I1 is the upper bound. So if the F statistics is lesser than the lower bound critical value, if the F statistics is lower than it's lesser than the lower bound critical value, then it means that there is no long-run relationship among our variables. If F statistics fall below the lower bound critical value, then there's no. If it falls in between the lower and upper bound critical values, then we conclude that that result is inconclusive. We can either say there's a long-run or there's a long-run relationship or not. So our result becomes inconclusive. But where we have our F statistics being greater than upper bound critical value, then there's a long-run relationship among our variables. So if you look at the F statistics we have here, you can see that it's if at, let me come in, let me look at it. We have, okay, so what you see, you see L1 here. These ones are the level of significance. So at 1%, this one is at 25%. At 5%, this is at 5%. At 10%, at 5%, and at 25%, and at 1%. So let's first focus on our significance level at 5%, and let's see if you take the F statistics, you can see that it falls in between the upper and lower bound critical values. So at 10%, it is inconclusive. Let's look at it from, let's look at the threshold of 5%. It's below the lower bound critical value. So at 5%, there's no long-run relationship among our variables that we are using. And let's move on to 1%. You can see that it's still less. So if you look at our variable, the F statistics, it's lesser than the lower bound critical value. So we conclude that there's no long-run relationship between upper emission and its regressors. So given this result we have here. So imagine our F statistics is greater than I1 critical, the upper bound critical value, then we can conclude that there is a long-run relationship among our variables. That's what we should have done. So if it is less than the lower bound critical value, the conclusion here is that there is no long-run relationship. If it falls in between critical and upper and lower critical values, it's inconclusive. Then if it's greater than the I1 or the upper bound critical value, there's a long-run relationship. So let's move on. So once there's no long-run relationship, then it means that we can only rely on the short run. It means that we can only rely on the short-run results. We cannot do a long-run analysis. But if our F statistics happens to be greater than the upper bound critical value, then there would have been a long-run relationship in that sense that we can go ahead to analyze or consider our long-run results. Okay, so let's presume, so here, in our case here, we can only rely on our short-run results. That's what it means. But let's look at the variables. The variable, let's now presume that we have a long-run relationship. Let's presume. If we have, then this one is the error correction coefficient or the speed of adjustment. So, like I said, it means that this means that the shock. This tells you the speed with which our model will restore to equilibrium when there's a disturbances in the regressors. Then we are presuming that there's a long-run relationship. So let me go ahead and explain the long-run result. Then if you look at the long-run result, we notice that aging population has a negative impact on carbon emission. But that was not significant at any of the threshold. Even though it was negative, that wasn't significant. So it means that the coefficient of aging population isn't different from 0. And in the case of population density, there's a negative relationship between population density and carbon emission. And that was significant at 5%. You will notice that unemployment, even though unemployment was negative, it had no significant impact. So that impact wasn't significant. The impact of unemployment on carbon emission, though it was negative, was negligible. It was not statistically significant. But we found GDP per capita to have a positive relationship between carbon emission. So it means that an increase in per capita income by 1% will lead to 0.092% in carbon emission. So that would have been the result explanation for it. But in our case, our F statistics is less than the lower bound critical value. So we conclude that there's no long-run relationship. So we cannot consider the long-run result. Then, so here, because there's no long-run relationship, we rely on the short-run result. Okay, rely on the short-run result. Okay, now let's move on with another approach. I'm going to use this to do one approach, and later we will also use the quarterly data to also do the same approach, but I'll be very quick with it. We're very quick with that. So now let's move on with the second method. The second method is just the same thing. Let's move on with the second method. Okay. So let's look at this. So with the second method, all what we do is that we determine the lags, the maximum lag, but just bring all of them. So that VASOC, then we write all our variables. Let me make it easier. Let's not waste time. Okay. So we type VASOC. We want to determine the maximum lag. So VASOC, then we type all our variables that we are using as one. We have, I remember I mistyped one variable like that. I still repeat that. Okay, so when we do this, when we determine the maximum lag for all the variable, we notice that the maximum lag is 4. Okay, 4. So the next thing we need to do here is that let's run let's look at an overview of how our ARDM model will look like. Just like a summary, like how it will look like. So let's type ARDM. Then here we type maximum lags. We put in the bracket 4. When you put all of them together, the maximum lag here. So this is the second approach. So we notice that the maximum lag for all of them is 4. So we put them in maximum lag. Then just just take one of the information criteria, which is alkaline or something, archaic or something like that. Let's move on. One of them. Just type that one. No, I still included what do you call okay. With this, we're being told that unemployment and GDP per capita have a problem with multi-coloniality. So we have to omit them from our estimation. So let's take that one out. Let's take that one out. Okay, unemployment and per capita income. They have a problem with multi-coloniality. So in this case, then why we should just exclude them? Let's exclude them here. Okay. Let's go back and type PASOK. Then we exclude unemployment and GDP per capita. And let's see what the maximum lag for them will be like before we come back to that. Okay, it was still 4. Okay. So let's now estimate it by excluding them from it. Okay. So we'll look at an overview of how our ARDM model will look like. So you can see that here, these are just an overview. So the next thing we need to do is that we need to then determine maximum lag for each. This is a second approach, another way you can look at it. We look at another way we can look at this one. So the next thing we do, we want to determine maximum lag for each of the variables we are using. So we type matrix, we type matrix list, and then E to bracket lags. So we want to be able to determine the optimal lags for each of the variables. So we'll do this. Okay, please bear with me. I'm coming. Let me try to fix this. This command. Wait. I'm coming. Let me try the first one again. Should be matrix or something like that. Matrix, yes. Matrix. Okay, we got it. So it was matrix. I was beating around. So when we type matrix list, then expected lags for each, we notice that the optimal lag for carbon emission is 1, and that of aging population is 2. The rest, they are all 2. So we can then go ahead to now test for run our ARDL. So let's run our ARDL model. Let's go ahead and run our ARDL. Okay. So in this case, let me look at a variable before we delete this. Okay. So in the second method, the optimal lag for carbon is 1, so write 1. Then that of aging population is 2. That of population density is 2. And that of, okay, let's add 2. We'll delete these ones. You have to know here that we have, okay, so we can just add our test to it so that it will just do it once and for all. Okay, so you should notice that we have omitted the life expectancy and also unemployment. We have omitted, at the variables we omitted. Yeah, we omitted unemployment and per capita GDP. Oh, I forgot to do estimation for, I excluded it. Okay. My estimation, I've excluded the life expectancy. That's why I've not seen it here. Okay. So now let's go ahead to this. Okay. So let's look at the, before we go back to talk, to discuss the long run and short run, let's look at the bound test. So we will use the F statistics in determining whether there's a relationship between our dependent variable and independent variables. So like I said, if the S statistics is greater than the upper bound critical value, then there is what? Long run relationship among our variables. So F statistics 3.169. Look at, let's compare that to all the thresholds, the upper bound critical values, and see. And see here, when is that 10%? It's not, when it's at 10, okay. So you still will, so here, also notice that our F statistics fall in between the upper and the lower critical value and the upper critical value. It's falling between those two critical values. So it means that it's inconclusive for us to say that there's a long run relationship or not. We cannot conclude for sure that there's a long run relationship. Now, in this case, because our F statistics fall in between the lower bound critical value and the upper bound critical value. If you look at our F statistics value, it's falling between this. So it's inconclusive. The result is inconclusive. So with this, like I said, this should always be, the speed of adjustment should always be negative and also significant. If you are doing the estimation, you notice that the speed of adjustment is not negative and significant, it means that your model is not correct. You shouldn't go ahead to analyze such a result, because what it means is that there's still a random walk when there's a shock to or disturbances in your variables in the long run, they are not able to attain long run equilibrium. So for it to attain long run equilibrium, then our speed of adjustment coefficient always has to be negative and also significant. In our case, like I said, okay, I learned there's a new test we can do. Let's click on this and see if that test will also, it also shows that our result is inconclusive. You see, A is reject. Okay. Yeah, so it shows our result is inconclusive. So with this, let's bear in mind that we always will pay attention to our speed of adjustment that is negative and significant before we can we can go ahead with our analysis. Because once it is not, then it means that any disturbances in your in the variables that you are using in the long run doesn't become stable in the long run. That's what it means. And with that, you cannot make any significant policy recommendation with that kind of variable. It means that whenever there's a strike, it just no more continues. There's no stability in the long run. That's what it means. So always we have to ensure that we have to ensure that the speed of adjustment is negative and significant. At this point, I will welcome your questions before we move on. I will welcome your questions. So Kwame.
Hello, Doc.
Hello,
thank you so much. Okay, thank you so much. But I'm not sure whether we should take a quick 5 minutes break and then you come back.
What's the time now?
Yeah, it's 4:03, and I think my people are already where they're down, so maybe I should take a break. So hello, family. Let's have like a quick water break for 3 to 5 minutes.
Okay, so let's so let's say we'll return around
we return around 4:08. Yes.
Yes, okay.
And I have to say this, I know it's a lot, and people are asking about the matrix, why do we need matrix and all those things. It's a lot to take in. So yeah, when you go back to the video, I'm sure things will be very clear. So let's take a short break.
Okay. Okay, let's when we return, I will take in the questions, then we'll move on.
Yes, please. Let's take a short break.
All right.
So we can have a short break. Maybe let me start my DJ work.
One focuses on introduction. We focus on simple regrets, such as awareness and explanation of the also select it's about panel data model. This document or we focus on surface data analysis and with Dr. Program. Looking at climate data analysis and 5 focuses on conceptual framework development and relational programming. Talking about design and conceptual structure. Then we will have all the programs online.
So 2 minutes more. So I think we should start getting closer to our laptops. 1 minute, just 1 minute to go. Oh, the video will be made available. So after the lesson, you can watch the video again. Trust me, ARDA is not very difficult. Just watch the video again and you'll be happy to do that.
Okay, Kwame, this time is up.
Okay, doctor, please, you can proceed.
Okay, so at this point, if anybody has a question, the person can ask. If not, we just go ahead and do the diagnosis test for
Okay, so
ARDM.
some of the questions was, why do you use the matrix? And what does it do? I think people want to know about the matrix reporting, the matrix listing.
The matrix part is just to, this is a different approach because if you notice, I've used two approaches here. So the second approach, what we first initially do is that we combined, we did a joint lag for all the variables. So we want to know the individual lags. So that's where the matrix came in. So the matrix there is just to know the individual lags for the variable that we are using. It's just an approach to determine individual lags for each, to determine optimal lags for each variable that we're using. That's it. Any other?
Oh, okay, thank you. So I think people were confused about the upper bound and then the lower bound, because the upper bound and lower bound is
the upper bound. This part is just this is just an approach that the Perseran 2001 actually came out with in order to be able to determine that the long run relationship among the variables. So you know that if the variables are integrated at the levels, see, if the variables are integrated at the levels, then it means that automatically there's a long run relationship. If you look at the, wait, let me try to explain that part. Okay, so look at the null hypothesis here. No level relationship, no level relationship. So if you do an integration test and all your variables are integrated at the level 0, I0, it suggests that there's a long run relationship. There's a long run relationship among those variables. If all your variables, if you do integration, if you do stationarity tests, and you notice that all your variables that you are using are integrated at the levels, then it suggests that there's a long run or there's a co-movement among your variables in the long run. That's what it means. So if you look at the F statistics, in instances where the F statistical value is not exact as the critical value, but rather fall below that critical value, then it means that there's no long run relationship. That's what it means. Because if your variables are integrated at the levels, it's a long run relationship. It's only when it is not stationary at the level, then you go ahead to find a first differential. You understand? Yeah, so if per the criteria, it means that if the F statistics is below the critical value for the lower bound, then there's no long-run relationship. I think this should answer that. But if the F statistics is greater than the differential, the I1, then it is significant. There's a long-run relationship. If it's in between, then it's inconclusive. It's inconclusive. You cannot either say there's a long run or not. Any other question before we move on?
Yeah, Doc, for clarity, when you are reporting the significance level, ARDL reports significance level for different significance level. For instance, you have significance at 10%, 5%, 0.25%, and 1%.
Mm-hmm. So these are the, yeah, I can hear you. The
and
5%,
in between any of them, yeah, Doc, I'm coming for a second. But in between, or for each of the significance levels, you realize there is a lower bound, which is the I0, and then an upper bound, which is an I1.
Yes.
Yeah, so for instance, if you want to report your significance level at 10%, then the first side, which is I0, I1, which has L_1, is the 10% level of significance, right?
Yes, yeah. You see,
you compare your...
Okay, let me
proceed. Yeah, so I was saying, so you pick the F statistics, and then you pick a significance level, maybe the first one, 10%.
At least you target 1%.
Yeah.
Right? It means that your confidence interval is 99%. At 1% error margin, it means your confidence interval is 99%. So if your F statistics is greater than the upper bound critical value at 1%, then that's it. It means that there's a long run relationship. There's a high long run relationship, a high significant relationship among your variables. So it's only when you notice that it is not significant at 1%, then you move on to this part. It means that the confidence interval is what? 75 point something. And if it's 25%, okay, that means, so here you have to check. This is 0.05. Okay, so it means that it is, let me see, 97.5%. This one, the confidence interval is 99.5%. So if you come to this side where the threshold is 0.25, and you notice that your F statistics is not greater than the upper bound, then there's no long run relationship. Then you proceed to threshold where the level is 5%. Then you also assess whether the F statistics is greater than the upper bound. So that's what we'll be doing, just be proceeding. So once you check from 1% and it's not, you move on to the next level, the next threshold. So you find, then you end at what? 10%. So if it is significant at 10% level, then your confidence interval is 90%. Any other before we move on?
So we take one last question from Shadrach. So Shadrach, kindly unmute yourself and ask the question.
Okay. Because we just have to run through this quickly before we
Hello, Shadrach.
We move on to the panel.
Okay, so Doc, I think Shadrach is now available, so we can move to the panel.
Okay, then let's move on. So, okay,
he's back. Shadrach.
Yes, what I'm saying is that when I attempt to run the model, the response I get is the factor variable and time series operators are not allowed.
Oh, you follow the command? Which one are you? The data set, we are using the second data set. I gave it to you guys last week. And we were using the transform data, where we transform the data into analog. That data we use. I think if you follow. So where did you get to when you had that error?
Where did you? When we got to run the ARDL model itself, all the other things were okay until it got there, and then.
So let me get to you.
I was not able to run it, and then the second formula too.
Have you checked? I'm coming. I'm coming. Make sure you have AIDN installed on your machine. Do you have it installed on your machine?
Yeah. I checked it and said it's installed.
So if with that, I don't think you should have problem with this.
Oh.
Shadrach, do you mind maybe we proceed?
Okay, I will. What I will do is that I will
Try
later
to-
will
Yeah,
use.
no problem. You can go on.
Okay,
No problem.
thank you.
Okay, I will use quarterly data later so that you guys can get it. Let me do the diagnostic test. Then after that, we'll use another one before I move on to the panel. Is it okay?
That's fine.
Okay, now let's move on. So the next thing here we need to do is that we need to run a diagnostic test to ensure that our results are consistent. So what we first will do here is that, the last time we discussed about those econometric problems, like problem with normality tests, you have to ensure that your variables are normally distributed. So we test for normality. So we want to be sure that our variables and the errors are normally distributed. So we'll do this, predict residuals. Predict residuals. Okay. Then after we predict the residual, we'll use the Shapiro and Wick test for normality test. So type SW Wick, then residuals. Okay. So if you look at it, you notice that it's our errors are normally distributed. If you find the p-value to be significant, then it means that it's not significant. It means that the errors are not normally distributed. But here, our p-value here is greater than 5% and also greater than 1% or 10%. It suggests that the errors are normally distributed. We don't have problem with normality. And we don't have normality. We don't have problem with our variable not being normally distributed. Now let's move on. So our errors are normally distributed and also independently and uncorrelated. Now let's move on. Let's look at serial correlation. So let's look at serial correlation. Here we want to check whether the previous errors does not correlate to the current errors. So let's look at the serial correlation. So here we type estimate. Oh, where am I? Estimate. Oh, sorry, what's this? Okay. What's happening? What's happening here? I'll be challenged with mine. Okay, so let's do this. Let's type start. Oh, why is it when I type nothing comes? Please wait a moment. I don't know. I try to type something that is not coming. Okay, wait. Let me put it somewhere. What's happening to my STATA? Which was this? If you can see, I think I'm having problem with the command bar. Mine is not responding. I don't know. Coming. From this. Kwame. Hello, Kwame. Can you hear me?
Okay. Yes, please, Doc. I can hear you. I think you
I'm
have something like a picture, so I'm not sure.
Oh, really?
Yeah.
Oh,
like you see, your cursor has turned into.
Yeah, I speak a certain picture or something. Where is the where from this?
Yeah. So try to.
I'm coming.
Just
please a moment. Let me try and click on delete.
Yeah.
From that picture. I have to be very careful.
So still have it.
I am trying to get it deleted.
Can you press delete on the keyboard list?
Okay, no. I tried that. Why from this?
And then you delete it.
Okay. It's still not. It's still. Okay.
And backspace is also not deleting.
Yeah. Backspace. No, I don't know where from this thing. From this. Why did I press those of you? Okay. Oh, still.
Okay, so.
Well, please ask them to give me some moment. Let me try and figure this thing out.
Okay, so everyone, let's just see.
If not, I have
Okay,
to
so-
launch. I have to launch a
can
new
you-
STATA.
Yeah, but
With
can
anybody-
you select it when the cursor turns into the cross, and then just select when
Okay.
it turns into cross? No, like
Okay,
the cross.
then delete.
Yes, if it doesn't delete, can you try the Control-C to cut it off?
Control-C. Wait. Those
It's not
IT
working.
guys is not working. I don't know where from this. The
Okay,
IT
so
guys here should try and help me out to get this thing off my screen. From this thing.
oh, can you press escape? Press escape, let's see.
Escape is not working. I don't know, it's a picture, but I don't know why this thing is on.
I'm not sure. So how about maybe we move those
Okay.
papers?
Okay, it's done now. It's done. Now let's go on. It's done. Now let's type a start then B Godfrey, comma lag 1. Then enter. This command isn't working. Okay, I think I miss some letters somewhere. Okay. So if you look at the serial correlation, the P value, the test, there's no problem with serial correlation. We don't have problem with serial correlation. Which is good. Now let's test for homogeneity of our variance. So we want to make sure that our variance is constant. So let's look at heterostochasticity of the homogeneity of our variance. Let's type this. Stat. This thing. I think I caused this. It has come again. It has come again, Kwame. I caused this. Where did I press the distinct up? The command is not responding with. That thing has come up again. I think it has to do with some of these things. I press somewhere. I think I pressed somewhere and I found it.
Try the escape, let's see, and just.
I just did a test right now. Still.
Delete or cards.
Okay. Oh, this thing is delaying me. I want to rush things with you guys too. If possible, should I restart a new STATA? So from this thing. Those of you who are IT bias can help me with this.
But if it is something you click, escape should take you out of it. But I'm surprised you said escape is not.
Yeah, it is not. Okay. Oh, sure. From this thing.
For the purposes of a flow, how about we go, like you relaunch another STATA and then we go into the panel? Or you still have more to do with the AI?
Okay. The thing is that with the particular it has to do with the STATA itself. If I press to launch a new program, then this thing pop up.
How about double clicking on the results screen? Let's see something.
The history. No, this diagram is just taking me
like
everywhere. That picture till is taking me everywhere I click it. Wow.
Even when you double click?
Yes. Okay, please let me try to. Oh, my computer is hard.
Like the latest should make it for me selected when the start time close. Yeah. But getting other suggestions like Control Z.
Control B.
Z, like Control Z as in undo.
No, Control T is also not working. Oh, too bad.
But doctor, you see when you put the cursor on it and it becomes that cross with the circle.
Yeah. It's not this.
Yeah. Yes.
Then
click
delete.
on it. Click just one. Click.
Yeah, I click on it.
And then
delete.
click on delete.
Yeah, it's not.
On the key. Okay. How about right click? Right click. Let's see. Is it right click?
Yeah, it's not.
Okay.
Okay. Can you log me? Let's see. It's not me. I'm coming. Please give me a moment. Let me try it.
Maybe relaunch the STATA.
I'm even trying to relaunch it.
It's not relaunching also.
Yeah. It's like that thing is sticking in.
Pause to close then, like Alt Control and delete. Alt Control delete. Your hand on Alt Control.
Yeah, that's where I am now.
Yeah, so click on STATA and close.
It's not closing.
No, just click on the STATA.
Give me a moment. A moment. Let me try and do something for you.
You know, from here, when you click on STATA, you can force to close it. Hello, everyone. Okay, so I'm going to unmute everyone, and then if you have anything we can talk about while the doctor tries to fix the problem. So everyone is on mute in case you have something to say. Okay, so I think so far no question and all concerns are good. I saw one question in the chat box that was asking if we could go over stationarity of your data again. And we did how to test for stationarity from the first lesson we had and even the second one. For your time series, the point is your data has to be stationary. And that is why we use the Deakin-Fuller test to test if your data is either stationary at first level, which is L1, second level, L2, or third level, mostly. Please, I have unmute everyone, so you have to click to unmute yourself. That is what you are supposed to do. Please try to unmute yourself because you have the option to unmute yourself.
Okay,
Hello.
thank you.
Okay.
Yes, can I come in?
Yes, please. While we
Hello.
wait for
Yes,
people to join.
yes. Thank you very much. I was a little bit concerned with regards to the matrix
Oh, okay.
because from last week presentations, if we want to do comparison between the income, as he rightly stated, the income and your expenditure, he was using regression analysis. But now I want to know, why are we using matrix, or in which type of analysis can we use the matrix?
Oh, okay. So if I got your question, last week we were looking at simple regression, the OLS. We're looking at OLS and stuff. Today we are looking at ARDL. And for the ARDL, you can use it if you want to check for long run and short run analysis in your data. And also if your data is not stationary at maybe first level, second level, those things. But what we are trying to do with them. Oh, hello, doctor. You are back.
I'm back.
Okay,
I think
so
I try to rush things through so that things will work for us.
Okay,
So,
let me do the right thing and bring you back.
I'm trying to share my screen. Are you online now?
Okay, so kindly hold on for a second, girl. I'm making you a co-host so you can do that. Yeah, so when we are doing the matrix part is only for you to list the lag levels of your individual variables, because the ARDL takes into account your variables, the levels. Okay, so the matrix we are looking at here is not an analysis, it's a listing. It's just for you to print out the levels.
Yeah.
I'm not sure if it is clearer now.
It's just to determine the optimal lag of each variable.
Yes, but we determine the optimal levels using the VASOC with all the variables combined, and it gave us that the maximum is 4. But we have to know if the individual variables, the level at which we have their optimal lag levels, and that's why we use the matrix.
Yeah.
First, we determine the optimal lag levels, putting all together, and it says the maximum among all the variables is 4. Now we want to go ahead and we want to know the individual ones. So we use the matrix list, the E lags, and that one will tell us that the first variable, maybe it is 1, the second variable maybe is also 1, the third variable it is 2. So it lays them in a matrix form for us. I'm not sure if you are with me on this. Doc, can you please share your screen so that you take over? We can address this question also in the chat group after for more clarity.
Okay. Let me share my screen now. Okay, so what I did, I just did a quick run of the model so that we are at the same space. So let me do a quick one, predict residuals. I've lost my predictions, the estimation, so it's a quick one. I'm just trying to bring back the residual, the tests, the diagnosis test that we did. So let me be quick with them. Then we did a residual test, which is estimate serial correlation test. Serial correlation test. Let me record that quickly. Now go on. We'll soon move to the panel. So then let's try what is it called? Homogeneity of the variance test. That's what I was about to do, and I had issue with my stuff. Okay. So that one, a STAT HETT test. So you also notice that we don't have any problem with heteroplasticity, or our variance is homogeneous. Then the next thing we should do is that we need to also check if we have problem with our model specification or whether we omitted other variables which are important to this estimation. So that's why we are looking at whether we omit other relevant variables. Look at that. Estimate OV test. Okay, so you can notice that also the p-value is not significant, so it shows that we haven't omitted any relevant variable. So we don't have any problem. The next thing we have to do is that we have to check whether our model is stable. So let's look at the stationality test of our model. That's the recursive errors, whether the errors that happen to our system makes our model stable over time. So let's look at the Kusum test. But before we do that test, if you don't have this package in your STATA, you have to install it. So we type SSC install Kusum. These are recursive cumulative sum of errors. So Kusum 6. Let's do this before. Okay. So if you don't have that, you have to install this. Then after that, we type Kusum 6. Then we write all the variables we use in our model. So in this case, we begin with the dependent variable. We'll move on to aging population. Then we have the next one. We have population density. Then we have urban population. Yeah. Then comma. Then we write CS into brackets Kusum. Then we write LW, the lower part. So LW, open a bracket, lower. Then UW, open a bracket, then you write upper. You close it, type enter. We have a problem with our variable. Wait. Okay, I think let me check which variable. Aging population, okay, aging population. I think I didn't write it well. Okay, so we wait. Okay, so what you have to understand that with this plot you see here, this is our regression plot, and the threshold there is 5%. So if this plot go outside this bound, any of this bound, it means that our model is not stationary. So for our model to be stable, and for our model to be stable, then the plot always has to lie in between the upper and lower bound to say that our model doesn't have problem with stability. So if it's outside any of the bounds, then we conclude that our model has problem with stability. It's not stable. But in our case, you can see that the plots fall in between the upper and lower bound. So our model is stable and our results are consistent. That's the test. So you always have to do this. If you do the test and the plots go off any of the bounds, then mean that the model is not stable. Okay, we're done. Kwame, at this point, we can take some questions, then later we'll move on to the panel. I try to, maybe later I'll come back to use the quarterly data to do some estimation for you. Can we move on now, Kwame?
Okay, Doc. I think, I'm not sure if there's any question. So we can allow for 1 or 2 questions.
Okay, if there's a question, let's take it then before we move ahead to the panel.
There's no question so far. So I think, okay, can you repeat the last step? Okay, someone wants you to repeat the Kusum test. So
the Kusum test, the Kusum test is used to determine the stability of our model. So if you do this test and the plot move outside the bounds, any of the bounds, it means that the model is not stable. For it to be stable, it has to be within the upper and lower bound. So if you look at this diagram, our plot is in between upper and lower bound, which suggests that our model is stable and the results are consistent or robust. That's what I mean. Any question?
Okay, so no other question. Doc, I think you can, if you want to move to the panel data, can we please have like a 5 minutes break to wind up the ARD and then we come and start the panel data?
I think.
Okay, so I think we deserve some 5 minutes break.
Because we don't have much time, I think I was thinking we should rush through the panel. We don't have much time on our side. Can we run through the panel? For the panel, we have a lot to do. Can we run through the panel?
Okay. So please let us take 5 minutes break and come back. We beg you. So let's have a quick 5 minutes break, okay? Please,
okay.
Just stretch, drink some water, and we come and start afresh with the panel data. So we come back at 4:48.
Okay.
Can you please remove the data so we can see the comment you use?
Doc, can you please close the graph for the command to show?
Oh, the command. Okay, wait. Let me hide this graph somewhere. Can you see the command?
No, like you close the graph and then the command.
Yes, close. Yes, close the graph.
Yeah, it's taking off. So I think it's clear.
I still see your graph, so maybe it will take some time.
You still see the graph? Really?
Yes.
Okay. Okay.
So maybe like cancel this.
Now it is okay.
Yeah.
Now it is okay.
Okay. In calculating the optimal lag levels for variables, the model indicates one unemployment, but he chose two. Are we sure?
Oh.
What happens if the model is not stable?
Oh, if the model is not stable, then it means that your results are not robust, because this has to do with errors that occurs the variable. So if it is not stable, then you need to use a different model.
So please just get some water to drink.
I have a question.
I'm listening.
Yes. Thank you very much. Thank you for a good lecture, but I have a question. It is possible to have variables. Some of them are stationary at level, others are stationary after phase difference, and it's okay. You conduct autoregressive.
Yes.
As you have said.
Yes.
Then,
go ahead.
Yes. Then after conducting autoregressive distributed drag, you failed to get long-run relationship, and also the results are not indicating the presence of even a short-run relationship. What to do? What does it imply?
If your bounds test doesn't indicate long-run relationship, it means that you can rely on doing a short-run analysis.
Yes. Then if the short-run also is not there is no short-run relationship. Well,
no.
Is it possible?
The bound test, you see, the bound test, it's you do the test to confirm whether there's a long-run relationship. So once the bound test doesn't indicate that there's a long-run relationship, it means that you can only rely on doing a short-run analysis. You get that? Like that one, you can rely on doing a short-run analysis. In this case, you can use other models like VAR. You can rely on doing VAR. VAR. Once there's no long-run relationship, then it's appropriate for you to use VAR. Or VAR is for long-shot. Yeah.
Thank you very much.
Okay, so we have 30 seconds, so please, let's get closer and we will start the panel data analysis. Unfortunately, we spent 2 hours on ARDL, but I think it's okay. Wherever we end with the panel data, we will continue our journey from there. Okay, Doc, I think you can take over for us.
Okay. I think let me look at this. Let's do this. I'll just be I'll show you something quickly. Then we'll move ahead. We'll go ahead to do the estimation, because I wouldn't want us to spend my time on the PowerPoint. Maybe later I'll share that with you. So what you need to understand here is that let me run it through quickly. Let me share my screen. Okay. Okay. Can you see my screen now? I've just changed that. Okay.
Yes.
Okay, so let's look at the panel. This one will just be a quick. I will not present a lot of the things, but I just want to let you know what panel actually means. So if the panel data actually has to do, it comprises of a cross-sectional data and also a time series data. You know, when we talk about a cross-sectional data, the data you survey at a particular point in time. So that's a cross-sectional. So most of the survey studies, the data you get from, let's say you are studying an industry or a household. So those data you get are just cross-sectional. Then with a time series, like I told you, data you collect over a given period of time. So the panel data actually comprises of these two. So it's more or less like a two-dimensional type of data. You look at it from cross-sectional and also per time. Let me show you this. I will not walk you through this, the reason why we use this, but we'll look at this one. If you look at this graph here, you see that. So this actually gives you a whole summary of the panel data. So we have our cross sections and also the time series. So if we say our panel data is balanced, it means that there's no missing value. Okay, it means that when you take the panel data, there's no any missing series in it, then you can say that our data is balanced. So whenever you happen to find a missing observation, then your data is not balanced. So normally when you are reading some of the statistical or the analytical approach, there are some of them that if your data set or your panel data is unbalanced, you can also use them. Some of the techniques can be used for balanced data and also unbalanced data. So you have to take notes when you are doing further readings. So in instances where there is no missing data, then your panel data can be classified as a balanced one. Now let's move on. I will not walk you through this PPT. Maybe later I will share them with you for further reading. Let's move on to our analysis. Let's try this. I give you some data set. Let's look at data set 3. Data set 3, I gave you some data set like that. Yeah. Data set 3 for panel analysis. We're going to use that one. So we're going to use that. So please open that and Control A. You copy. Let me launch. Okay, clear. Let me clear this. Okay. So I clear the data. Now I'll paste. So you paste, you right click and you paste special, you select, treat the first row as variable names, and okay. So now we have our panel data. So these are cross sections. The cross sections here are these are the cross section. This is the countries involved, then the year. Let me get back to this graph is still here. Okay. Now once we have imported our data, now let's declare that our data is, let's set the time. Let's declare our data set, panel data. Let's do that one. So what you need to do now is that you type generate country one. So we are going to group our countries, the countries as a group. So generate country one equal to group. Then country. So let me get back to, if you look at our variable, we have what country there. So the countries, that's what we're grouping them. We're grouping all the countries as a group, group them as one. So then after that, we declare that our data is panel. So set country one, year, and then year. I think when you type year to income. Okay, so we've now declared our data set to be a panel data. We have declared that. So what we're going to do now is that we are going to do the pool regression, then fixed effect, and then also random effect. Then later, what I would then do is that we also will look at panel data. We look at the fixed effect when we consider demi variables. So if we allow the independent intercept of the cross sections to show, we'll involve that one. So let's first do this. We're first going to, so I'll do the first one that I will involve it will not involve the demi variable. Then in our second approach, we'll come and look at when we include the demi variable in our fixed effect approach. So let's look at this. First, we do a full regression. So xi column, then regress. So with our data here, we are looking at impact of climate on well-being, okay? Impact of climate change on human well-being or human development. So here we have remittances, trade, urban population, then GDP per capita, carbon emission. Our dependent variable here is the HDI, that is the well-being, a proxy for human well-being, then temperature, then rainfall. So we're looking at how climate affects our well-being or human development. So let's regress. So this one, the first estimation we're doing is for full OLS. We'll write IX, then column, then regress. We begin with the dependent variable, which is lane ATI, then temperature. And let's begin with the temperature info. I'll just consider a few of the variables. If there's too many, I'll just consider a few of them. Then we look at carbon emission. Okay, now let's look at per capita GDP. Per capita GDP, so our economic growth. And I look at remittances. Okay. Okay, let me include trade, then I think we have to do all of them. Okay, so this is our full OLS regression. Just type. So this is our full OLS regression. The next thing we do here is that we test for the fixed effect. And the next thing we do, I'll walk you through everything. We test for fixed effect. So don't worry, I'll come back to you. You noticed? Oh, okay. I repeated something. Okay. How come? Okay, let me rerun the model again because I think instead of rain, I repeated temperature twice. So let me run it. Away from this one. Temperature. Rainfall. Okay, rainfall. Rainfall, yeah. Okay, so now this is okay. Then the next thing we do is we do a regression for fixed effect. So the fixed effect here, we use XT regress. Let me bring this. So there's XT regress, and then comma EF, which stands for fixed effect. Or from this variable. Sorry. Okay, so this is our fixed regression. So let's then go ahead to do our random regression. So with the random regression, the same as the fixed effect, just that at the end we make it RA. So once we've done this, I'll come back to the analysis, but I want us to do other estimations, then we attempt to do. Once we've done this, the next thing we have to do is that we have to know which of these techniques is it appropriate for us to use to estimate our model. So the next thing we are going to do is that we are going to choose between the random effect and the pool regression. We are going to do that. But here we will do this on assumption that your regressions doesn't have problem with serial correlation. It doesn't have problem with the serial correlation, homogeneity of the variances. You have to make sure those errors don't exist before you can go ahead to do this test. So now let's move on. So let's do a test. We are going to use the Bruce-Pagan LM test to decide between the random test and also the OLS test. So the null hypothesis, let me do the test first. So the next, what we need to do now is that we need to type STT test 0. STT test 0. This is for Bruce and Pagan. So this is that. With this test, the null hypothesis is that OLS is appropriate. And if we find the p-value to be significant, then we reject the null hypothesis and then conclude that random effect is appropriate. So here we can then we then will settle on random effect and say that the result of the random effect model are what? Efficient and consistent. So now let's look at we're choosing between fixed effects and random effects, because we have not been able to conclude that it's appropriate to use a random effect model instead of the OLS. So let's now decide between fixed effects and random effects, which of them is appropriate to produce consistent results for model. So what we have to do, we have to use the Haussmann test. But what I was, okay, wait, let me rerun these models again so that I can save them. Okay. let's type husband. I think it's correct, husband. Then fix it. Let me run this. I want to run this. Then let's save this result. So store fix, store fix. This is our fix. Yeah, fix regression model. So store fix. Okay, it's already stored. Okay, then once it's stored, then we can now go ahead and do a test. Let's test for husband. So husband, then fix, and then random. Oh, okay, wait. Not valid. Okay, wait. I'm trying to store the store. Okay, we store the fixed result. Let's do for random test. Then let's store the result of the random test. So here, random. We name the result, the random test random. Okay. Now we go ahead to do our Husman test. Okay. So here, with the Husman test, the null hypothesis is that the random effect model is appropriate, while the alternative is that the fixed effect model is more preferable. So if you are to choose between the random effect, given this result, that means that the results, we can conclude that the fixed effect results are sufficient and consistent, and therefore we have to use the fixed effect model in our discussion. Any question from here before I move on? Is there any question?
Yes, please ask a question.
Okay. Please ask your question.
I want to even ask from the beginning because I have my data set, but I don't know why when I import them, they all come as string variables.
Oh, really?
But it's not this data set. It's not this data set. It's just my own.
I shared the data set for this estimation with you. So I think you need to use the data set we're using now. Then later you can attend to your data to see if you have problem with how you prepare your data in Excel.
Okay, and now if probably in your data, what I downloaded, they are like null values. Are you supposed to remove them manually from Excel before importing in STATA, or there is a code that can help you to remove all the null values?
That one, I don't know. What your question again? I don't seem to understand your question. Please ask your question clearly.
I'm saying when you download probably data from a platform, sometimes some places come empty and they can put null, like NULL.
Oh, okay. I think
yes.
I got down. You see, prior to the estimation, I said that the panel data, we have balanced data and also unbalanced data. If you look here, you see that once I declare, I'm coming. See, once you will notice that our data set is what? I'm coming. Wait, let me show you something. Okay, wait a moment. I just want you to draw your attention to something. Okay, so if you notice that once I declare our data set as panel, it shows that it is what? Strongly balanced. So what it means is that in our data set, we don't have that problem you are having. It means that there's no missing variable. If you have that now, the missing variable in your data set, it means that your data set is not balanced. So what you have to understand is that given with the techniques, some of the techniques doesn't work well with the unbalanced data set. So you have to take note. That's what I was trying to draw attention to. That some of the estimation techniques, your data set need to be balanced before you can use them. There are some data set, if they are not balanced, then you cannot use a certain estimation techniques. So maybe that's the challenge you might be having. So ensure that your data set is balanced in a sense that they shouldn't be having that non thing. Then it will work. I hope I've answered you.
Okay, yeah,
Yes. I have a question.
Okay.
I have a
I'll
question.
take this, then we'll move on.
Yeah. Then, like after conducting your autoregressive display data, you did some robustness. You did some robustness. Like I remember Kushum. I remember some.
That's the ARDA test you were asking.
Yes. Then after conducting Hussman test and maybe you choose a random effect model, then what kind of robustness for confirming it is finished to represent like that? So
No, it means that, you see, wait, let be there. You see, I did estimation for 3 techniques, which is the pool OLS, the fixed effect, and the random effect. So
all right.
What we're doing here is that we want to select which of these estimation techniques is appropriate for you to use. Yeah,
right.
You have to decide which of them is appropriate. So if you look at the results, I'm coming. We did wait, let me show you this result so that you follow up. If you look at this test, the Bruce and Pagan LM test, it is for us to choose between the pool OLS and also random test. Here we are just, with this test, we are deciding whether we should use random effect model or the pool regression model. So if you do this test, so with this test, the null hypothesis is that it's appropriate for you to use pool OLS. And the alternative is that the random effect is more preferable. So with our p-value, we reject the null hypothesis that pool OLS is appropriate and then use a random effect. So with this test, it means that it's appropriate for us to use random effect model. But we also have the fixed effect here. So we then have to then do a test to decide whether we should go ahead to use the random effect or fixed effect. That's when the Hussman test comes in. So the Hussman test really comes to confirm whether we should go ahead to use the random effect or the fixed effect. So with the Hussman test, we are only using the outcome from it to decide which of them we should use. That is the fixed effect or random effect. And with the Hussman test, the null hypothesis is that it's appropriate for you to rely on the random model. And the alternative is that it's more preferable or it's appropriate for us to use the fixed effect. So if you do the test and the p-value is significant, then we have to reject the null hypothesis that it's appropriate for us to use the random effect, but rather rely on the fixed effect. So it's just, we are just doing model selection. These things, so at the end of this, what we've done, it means that we have to use fixed effects. So imagine in your work, in your studies, you have done all these tests. Imagine you are doing the thesis and you have done all these 3 tests. In doing your analysis, you don't rely on the result of the random effect and the pool regression, pool OLS. You have to rather rely on what the fixed effect result in doing your result, because the Hussman test says that the results of the fixed effect are more efficient and consistent.
Yes, thank you.
Okay, then can we now move on now? So you can see that if you look at the results, I'm coming here. Okay, let me try and go through with the analysis. I think, which one is this? Okay, this is the pool OLS. But you see, at the end of our test, we have to use the fixed effect. So let's let's look at the fixed effect result. So with the fixed effect result, we noticed that all our variables have what? Significant, with the exception of rainfall. So all our variables have what? Positive relationship with human development. So rainfall does not have a significant impact on human development, but temperature and the rest of the other regressors have positive relationship between there's a positive relationship between human development and our other regressors, with the exception of rainfall. Okay, so I want to run through this. If you understand, let's now move. Let's look at. I wanted to show you something. So if you look at our results, you will notice that we don't have a constant. There's a constant here, but this constant is fixed. So let's look at the time invariant, where we have different intercept for the individual countries. Okay, the countries. Let's see. Look at where we have different intercepts for them. And those intercepts here, intercept of those individual countries are what? Time invariant. What it means is that they remain constant over time. They don't change. The value of those intercepts do not change. So we're going to consider a demi-variable grouping. So let's look at something. So that will be our third approach we are going to use. So we are going to look at least square demi-variable. So we are going to introduce a demi-variable into the fixed effect model. That's what we are going to do. Let's try to look at that. So please take note. This is a second approach we are using with this. It's a second approach. So with that one, with the second approach too, we go ahead to run the full regression, the OLS, okay? We'll go ahead to run that. Okay. So that one, the type XI, then column, regress, then dependent variable. That's for full OLS. So once we do that, then now the next thing we're going to do is that we are going to introduce a cross-sectional time invariant. So let's say in your data set, okay, let's say in your data set, the countries or the cross-sectional identifier belongs to certain groups and certain group or association. So it means that let's say you are looking at countries that are conflict prone and those that are not conflict prone. Okay, let's say you are dealing with countries that are conflict prone and countries that are not conflict prone. Let's say countries that they have excess resources, natural resources, and maybe others that don't have, they are not rich in natural resources. So we have a two demi-variable here. And these variables are time invariant. They remain constant over time. So let's look at instances where we have that thing. Let's introduce that. Let's type this. So we'll type, we do a full regression. So with that full regression, the next thing we're going to do, we are going to introduce a time invariant. So it means, let me show you the data set. So these are the countries we are using, okay? These are the cross sections. So these are this cross section identifier. We have identified them, see 1, 2, 3, and other stuff. So the 1 is for China, the 2 is for India and other stuff. So let's get back. Now we are going to introduce that cross-sectional time invariant variable. So it means that there's a demi-variable. There's that demi-variable there, the binary demi-variable there. Let's introduce that. So we have I. After we write our regression model, we add I dot the cross-section identifier. So if you look at our studies, we initially we generate country one. We generate country one. So our identifier here is what? Country one. So here we write country one. Okay. Then the next thing we do is that we run the regression. Okay, so this is what you need to understand here is that here we are looking at the fixed regression in a different way. That's a different way of looking at what? The fixed regression. Because I didn't get time to present the PPT for you, I would have shown you them how mathematically this thing is represented. But we are looking at country-specific intercept. And so this country-specific thing is what? Time invariant. It means that it doesn't change over time. So I create an example for you, like, let's say in your data set, some countries are conflict prone and others are not. So we have you code 1 for countries that are conflict prone and 0 for countries that are not conflict prone. So that's time invariance. We're looking at that one. So what you have to understand, and this estimation here that we've done is the same as running the fixed effect model. So let's try and confirm whether the result we've gotten here is not anything different from the fixed effect. Oh, wait. I think please wait. I repeated, I didn't include the rainfall. Okay. Okay, so now we have the rainfall. So what I'm saying here is that the result that you are seeing here is not different from a fixed effect model. Even though you have included the time variant, the cross-section time invariant, it is not different from just running a normal fixed effect. So let's try to look at that. Let's run a fixed effect model just to compare, to make sure that the results are just the same, just to confirm that the results are the same. So we do this, I'm just running a fixed effect model and compare that with instances where we have, and compare it with the least square demi variable model, which is the same thing. So let's look at that. Just trying to do this. Okay, so if you look at the coefficient here, coefficient you see here, and compare that to what we have, they should be same. Should be the same. I'm coming. They should be the same. It has omitted one in our case. Yeah, it has omitted, but they're the same. If you look at the result, they're the same. If what you see here is that the full regression model has omitted it's just a default. It has omitted the temperature. I don't know. Yeah, I don't know what happened with that. But the temperature. Oh, sorry. I didn't include it. I think that's why I didn't include it. So let me run the model again. Let me run the model again. Let me include this one. Yeah, this one include. Okay. Right. Well, I'm running the LSDV. LSDV. Include country one. I didn't include the temperature in our stuff. Okay. Let me check so that this time around I'll be sure. It's Command X. Oh God. Oh, okay, XI. Semicolon. Okay. Okay. So you notice that if you compare the SDV model 1, in this case, we are looking at the cross-sectional time invariant. Cross-sectional time invariant. If you're looking at the results you see here, and compare that with a usual fixed effect model, the results are the same. Look at it. This is a fixed effect model. It's just the same thing. So LSDV model 1, you notice that the results that you get is just the same as our usual fixed effect model. If you try to look at, because we are looking at fixed effect in a different way, we are looking at where the countries in our data set have individual country-specific intercepts. So we're looking at that. And that intercept are time invariant. It just remains constant. Okay, so let's move on to the instance where there's a time factor. We're looking at as the time changes, the time, we are looking at time, which is here. And we are looking at when the year changes, the country-specific unobserved errors that we didn't include in our model should remain what? Constant. Should remain constant. So let's do a regression. In this case, we are considering time. So here we are looking the first model, we consider just a cross-sectional time invariant, where the countries have grouping, the demi groupings. Let's look at that with respect to time. So as the time changes, then country-specific time invariant doesn't change. Let's consider that one to look at it across time. So here we have I and year. Okay. This is, so you notice that I have a lot of years. Yeah. So we're looking at how this the time country-specific time invariance for individual how it is across how it behaves across the year, but how it's behave across the time span. Okay. Then the next thing we need to do is that we have to look at our fixed effect model. We have to look at our fixed effect model considering time and space. So here we are going to consider, we are going to look at how our model will behave given the demise of the country and also within the time as the time changes. So here we'll have our pool. This one is the LSDV3 model we are doing now. So the next thing we do here is that we involve country. So we are looking at the time and space invariant. Okay, time and space invariant. So the space here is our course session. Just look a little tedious when you are doing this, but just follow. I hope I make it so easy for you to understand. So here we just type, after we write our normal pool regression, then we include the year time invariance. We include the time invariance and the cross-sectional invariance variable, which is the countries. Let's run. Okay. So now that we have done, this one is the LSDV model 3. Now what we need to do here is that we have to then choose between LL1 and what? OLS. LL1 and what? OLS. So we are going to do that by looking at the restriction. And we are going to consider the restriction in the model 1. That's the LSDV, the restriction that we have in that model as compared to the pool regression. Then we use that one to determine whether it is more sufficient for us to rely on this model, or we use the pool OLS. So here we are going to, if you look at the pool regression, okay, this is the pool regression. Okay. If you look at the pool regression, what is that? Yeah, this is the pool regression. If you look at the pool regression as compared to the LSTV1, the difference there we have is what? The cross-sectional time invariance. So That's what we are going to look at. We are going to compare that and then decide whether which of them is more sufficient and consistent with the results. So let's try this. We'll do this. Let's do a test here. Test. So in this case, we are going to write what do we have to do? Let's write test palm. Right, test palm. Then we look at the restriction. We consider a restriction in the LSDV model. So let's first consider the model 1 and compare that against the restriction. So we take, if you look at the model 1, we have this. This is the restriction, the country restriction. So we are going to type that one. So test palm, then you type. It's a little difficult. Please see, follow. It's a little tedious. Country 1, then _2, space, _. So we just consider this, what we see here, this, the cross-sectional time, the cross-sectional invariance, that's what we're considering. So I'm typing that, country 1, _, _3, then let's move on. Country, I'll copy that and later we'll make it quickly. Country 3.1 _4. Okay, let me copy this and paste them so that's quick. Okay, so this one will be _4 _5 _6. Okay, 6. Then let me move on. Let me paste this again, and _7 _8 _9. Okay, so this is the cross-sectional invariant variable, time invariant variable here we have. So this, we want to test whether it is sufficient for us to rely on the LSDV model 1, or we use the full regression. Look at this. Oh, sorry, I have some mistakes somewhere. Country, okay. Country, okay. Let me see. Okay, country, I didn't write it well. Country, yeah. Okay, so I corrected it. Please, you take a closer look when you are also doing the same. What is that? Country _3 not
no E,
found.
no, the country, no E.
There is E after.
There's E somewhere. Oh, okay. Yeah, I said it. Thanks. Yes, I think that's causing that. Thank you. Oh, okay, thank you. I've seen it. Is this okay? Yeah, okay. Thank you. That's good. It means you are paying attention. So we're done. We just go ahead. Okay, so if our p-value is significant, so it means that our LSDV model is more efficient and consistent as against the full regression. Then the next thing we are going to do is that we are going to do a test for the year. So we do the test the year 1. We're going to test this against the time invariant. We are going to also, the model, that's the model 2. We are going to compare that against the OLS and see whether it's appropriate for us to use that. So here we type test palm, then we write this we consider this, yeah. So underscore year underscore 1992. Okay, yeah. Capital 1, I, then underscore 1993. Yeah. Underscore 1994. This will be a lot, 1994. 1994. Let me try and repeat it. Let me be pasting them and see so we can move forward. I'm trying to copy them and paste them so we don't waste time typing. Okay, so 1995, 1996, 1997. Let me paste again. 1998, 1998, 1999, oh, sorry, 1999, 2000, the year 2000. Okay, let's paste again. 2001, 2001. This is very tedious. This is very tedious, so please bear with me. Okay. Then 1992, 1992. 2002. Let's move on. Let's move on. 2003, sorry. 2003. On to 2004. So we get to 2020. Yes, I should have used a reduced data set with a short time span. That would have been easier. Okay. I'm getting. Okay.
But Doc, for practice purposes, we can just do the test parameter up to a certain threshold for a certain number of years for people to just understand.
Yeah. I think that's good suggestion. I'll take that. So let me do to some point, then I'll stop. Okay. Let's take this 2006. Okay. So like you suggested, let's end at 2007. Okay. Then we'll type enter.
2001 is repeated twice.
Really?
Yeah. But I think people understand it, so it's okay. Every one of them should be one.
Okay. So once the p-value is significant, it means that the model 2 is more sufficient and consistent as against the OLS regression. So what you will need to do here, if you can see that when you compare the LSDV1 and LSDV2, LSDV2 has the country and also has the time variable. So it suggests if you compare this, there's no basis for us comparing the model 1, LSDV1 and LSDV2 model to the LSDV3. But if we do for the LSDV3 as against the OLS, the results will be more, it will be sufficient and consistent. And that model that the literature suggests that it is rather more preferable as against the L1 and the 2. So here, the model 2. So because if you look at the 2, it will suffer from a linearity because that is, it just has to do with their grouping. It has it's time invariance. So here we rely on the 3. We are going to, so now we're going to say, we are going to now run our fixed effect model, okay, the fixed effect model. Let's run our fixed effect model now, okay. By considering this invariance, so fixed effect model. That's what we're going to run now. And here, we will consider the years as we consider the years, the year intervals or year time invariance. Then instead of us, if you look at the model 3, we have the year and also the cross-sectional invariance. So like I told you, when I did the model 1, I compared that to our usual fixed effect model estimation. Then you notice that it's just the same. So instead of rewriting the year, we will just write comma, then EF. Because when I did that, I'm coming, let me get you to this place. If you look at LSDV1, the result is just the same as scientific. This is fixed effects. And if you compare that with LSDV1, they are the same, okay? The estimations are the same. So in doing our final fixed effect estimation, we include the year, the time invariance, okay? So the country-specific time invariance, and here I'm saying that the country-specific time invariance is constant, maybe it's 0. Okay, so wait. Okay. So this will be our result. That's our fixed effect model that we were estimating our work. That's what we use. You get it now? So the next thing now we should do here is that we have to also run random effects. We have to run random effects quickly. Let's run random effects. Random effects. So what we're doing, we're looking at different ways the fixed effect will behave. So now we're running the random effect. Okay, so this is our random effect model. Now we have to decide whether to use the old, because we already done a test which suggests that they're using the fixed effect is more appropriate. So now we are going to choose between this fixed effect and the random effect. We are going to choose between this one, and also the random effect. That's what we are going to decide, which of them is more preferable for us to use to estimate our model. So we use Hostman test, then fix, then random. I should have saved the data. I'm sure to work this time. Okay. So if the Hostman test results, then it suggests that our fixed effect results are efficient and consistent. So our analysis would then have to base on what? The fixed effect model. Okay, we're done. Can we move on? I welcome. Can we move on? Can I do other estimation for you?
Hello, people. Do you think we should?
We're done with the round.
Yes, you can do another one. You can do another one.
Okay.
Command number 42.
Okay, now we're done. All the time, don't worry. After I run through, I'll give you. I'll make time for questions. So let me run the other models. Okay. So with this one, we just deciding whether we should use fixed or random effects. So that's the procedure you will use in deciding which one. But you have to make sure that in using this approach, your variables and your data set doesn't have problem of multicollinearity. And let me give you this. Look at this. Wait. I hope you guys can see my screen. I'm showing the PPT. Can you see that? Can you see my screen now?
Yeah. Yes.
Yeah.
Okay, so this is the pool regression. If you look at the pool regression, we have regression for individual countries, then we put them together. Okay, so look at this. Before you run this model, Let me show you this. I will later will try and share this with you. We have to make sure that you do this test. Okay, you have to do this. Just make sure that you don't have this problem in with your data. If you have this one, these three problem, multicollinearity and other stuff, those problems your data shouldn't suffer from this problems. Then you can go ahead to use your that. Now let's look at this. Let's look at a situation where your model, okay, your model suffer from this. Let's say your model, your data set suffer from multicollinearity, serial correlation, and also the homogeneity of the variance. It is heterogeneous. You have heterogeneous of your variance. If you have such a problem with your data, then it means that you need to use a different model, okay? You need to use a different model. It means that it's not appropriate for you to use the fixed effect or random effect. You don't need to. You need to use a different model. So let's look at instances where I will come back to this one and this. If you have such problems, what you are supposed to do, okay? It's okay now. So let's look at this. Let's assume that, let's try to look at this. Let me give you this. Let's try this. First of all, let's try the dynamic OLS. Okay, dynamic OLS. The dynamic OLS, there's a precondition before you can use the dynamic OLS. With the dynamic OLS, one of the preconditions is that your variable should be integrated of order 1, the dynamic OLS. Then also, there should be what? A long-run relationship. Long-run relationship should exist. Once your data set, the variables that you are using are integrated of order 1, and there is a long-run relationship among your variables they are using, then you can proceed to do estimation for DOS, okay? That's the dynamic OLS, So let's try that. What you have to understand is that the dynamic OLS is also robust. It's very robust to serial correlation and also endogeneity. Okay, let me show you this one. Endogeneity. Okay? And that model is more robust to this and serial correlation and that stuff. So you can, when you have such a problem with your data set, you can also use those. Let's look at how we can estimate those. I'll try to touch on a lot of them so that we can move quickly. But before we go, we do the DOS estimation. Let's do this. Let's install this command. Before we do the estimation for DOS, let's install this command. SSC install. I want to be quick. Install st DOS HM. Okay, let's install this one. Okay. I already have it installed, but those of you don't have installed that one. Aside that, you install SSC LTIM VIMATA. Okay, install that one too. Okay. So once you have this installed, then it's easy for us to do our DOS estimation. Once you have this installed, this is quick. So let's try to run that quickly. That's right, st DOS HM. Then after that, we run our model. And so you be st DOS HM, then you type the dependent variable. In our case, it's what? HDI, that is Human Development Index. Then you write temperature, rainfall, carbon emissions, then per capita income, remittances, and trade. Okay, so this will be our model for the DOS, just type estimate. Okay, so these are our results. This model is more robust to serial correlation and also endogeneity. So if any of your independent variables are heterogeneous, or you have that problem, then it's more appropriate to use this. Okay. So with this, if with the DOS result, you notice that temperature and carbon emission has a negative impact on human development, but the impact of carbon emission was not found to be significant at any of the threshold. And also, so you can see that even though they have a negative impact, all of them do not have, their impact is not significant. The impact of temperature and that of carbon emission, even though they were negative, they were not statistically significant. So their impact on human development is what? Negligible. It's not significant. Then we have rainfall. The impact of rainfall, even though it was positive, it was also not as significant at any of the levels. So it has no impact. Then we have income and remittances has a positive relationship with human development. So an increase in income and remittances will go to improve human development. The same as to trade. In the case of trade, an increase in trade will also lead to an increase in human development. So that's the explanation for the DOS. Now let's move on. I'm trying to run things through quickly so that I can grasp a lot. Now let's look at this. Let's look at instances where you have this problem. I was thinking of running. Let me try this. Let me try this one. Let's run panel ARDL model. Let's run that one, panel ARDL model. Let's try to run ARDL model. Okay. Then later I'll come back to deal with the other problems too. But all of this, after you have to know how to determine the diagnostic test before. I will do that for you before we use the panel. Okay, before we use the panel, let's look at this. Let's try to test for serial correlations before we go and do the panel idea. So let's try to test for serial correlation. So install this. If you don't have this, install STCD. Install STCD on your system. We use it to test for cross-sectional dependence. Okay, we use that one to test for cross-sectional dependence. Okay, so let's now test for cross-sectional dependence. So we want to look at whether any change in one country will lead to a change in other country. Okay, because those countries that we have grouped them in, we're analyzing, we want to see if there's any occurrences that are happening in those countries. Is it going to transcend to other countries that we have considered? So we want to see how these countries interdepend on each other. You understand? Yeah, you notice that if you are trading with one country, when there's high inflation in their country, it's possible they will transfer, you are going to import that inflation. So we're looking at that interdependence, whether it exists. If the interdependence exists, then you have to then use appropriate method to correct that error. So let's look at that. Let's type STCD. Then what we do is that we write our variables. Okay. Comment. STCD. Then write all our variables we are using. Okay, so these are the variables we are using. After you write it, then you type enter. And they're giving me too many variables. Why? Okay. I think let me take just a few of them and see. Check this. Okay. See. I don't want us to be doing them one by one. And, okay. So I've taken about 5 of them. Okay. So look at these variables. I think our variables were so many. So STATA was telling us our variables were so many. So I reduce it. So if you look at the variables, the p value is what? It's 0.00. So it suggests that there's a cross-sectional dependence among the cross-sectional units. Okay, there's a cross-sectional dependency among the cross-sections. So it means that any disturbances in one country will transcend to another country to have an impact. So we have to make sure that we use a model that will help correct this. Now let's run a serial correlation. So since I will use just 5, the serial correlation let's use just 5 variables. Let me see. So the serial correlation, let's start ST serial, then we use mind development. Let's type the variables. That's just the 5 variables that we use. There's no y there. Then temperature, then rainfall, then lean carbon emission, lean this. Okay, let's look at the serial correlation. Okay, I don't have it stored on mine. So let's install that one too. I don't have it installed. I think that's why it's showing that I cannot find that. So let's write, let's install that. Install ST serial. Okay. Why it's not ST serial? Oh. Okay. ST serial. I don't know why it's not. I'm coming. Let me check. Command if I see that. Okay. Let's get back. Let's try to do this. Oh, shit. I'm coming. I'm trying to hide get back to my command page. And on this. Okay. I'm coming. Oh, the help is okay. Let's try this. Let's try to run a regression and let's run a regression. Let's say fixed regression. Let's run it among fixed regression. Let's see. Then check. Okay, let me in our case. Oh, okay. Then let's type the serial. See if we can get that. This is not recognized. This command. What is happening is that some of the versions of STATA find it difficult to recognize some of the commands. That's what I've seen for some time now. But we can move ahead. Let's move ahead and look for heteroscedasticity, homogeneity of our variance. Let's move ahead and look at that. Later, you have to look for the command to do this test and look at that. So that with that, we first, what we'll do is that for us to write, determine the variance. Okay. Okay. We run a regression. There's a fixed regression, fixed effective regression. Then we type STT test 3. Oh, it's also not recognized. What's happening? Okay, let me see which mic. I think this my stuff.
Hello, Doc.
Yeah.
I think it's also possible if they install from the URL itself, like net from. I think I pasted the link in the STATA forum.
Oh, okay.
Yeah,
I don't know, but
it will
my
help.
command. Okay, I'm trying. It's getting installed. So I think this one is installed. So we run a normal regression, then test follows. Okay, so you notice that we have problem with a group heterogeneity. The variance is heterogeneous. So in this case, the next thing we have to look at it, we have to check whether our coefficient, the slope, is also heterogeneous across a session. So let's look at that. Let's see if our data is, our slope has that. So with this, I think I'm coming. Let's install this one. I don't want us to type in to be like we have not installed. It means I've not installed a lot of things on this machine. STH. That's we are doing the slope homogeneity test. We want to see whether our variables, our slope or the coefficient, regression coefficient, our panel regression coefficient is homogeneous or heterogeneous. That's what we're trying to do now. So let's install this on our system. I think I have not done that. I seem to be faced with this. So once we have it installed, we type STH. Then what we do is that we type all the variables that we are using. So just like we did for the one we did for, this test. Okay, let's consider up to trait and let's see. So STHS. Okay. Then just continue with the variables that you are using for the study. So the dependent variable and the rest, the regressors, continue that. Okay. So here, once the p-value are significant, it means that we reject the null hypothesis that our coefficients are homogeneous. So it means that our coefficient is what? Is heterogeneous. It means they vary across time, across sessions. So when it happens like that, when you have such a problem with your data, then what is suggested that it's important you use panel ARDM, or what we call pool mean group estimator, That's PMG, or better still, you can call it ARDM, panel ARDM, okay? With this, we are able to, with this model, we are able to do an estimation for long run and short run. And it's very robust to this point. It's able to take off these issues that we have above. So what we need to do is that we now going to run the ARDM model. Since our slopes are heterogeneous, so we're going to, and we have all these problems. So we're going to use the ARDM model, which is very robust to this econometric issue. Let's look at that. So please install this, type SSC install. I'm sure this is my laptop. This particular laptop have not installed a lot of stuff. So install STMG. Okay, let me add replace so that if I have it, to just replace it. What's that? this command. I'm coming. Let's type install. Install. Please do you have that? Install stpmg. Okay, let's install that one. stpmg. Okay, now I have it installed now. So what we are going to do, we now will go ahead to run our ARDL model. Okay, we can go ahead and run it. With this one, we don't even need to test whether there's a co-integration test or whatever. I can choose not to do all those kind of tests. Just after you've done your unit root test and you've done all these tests to confirm that these problems is in your data, you can then go ahead to do estimation for the full mean regression. And with the full mean regression, the assumption is that one of its assumptions is that the long run slopes are homogeneous across the session. So across in the long run, the slopes are what? Homogeneous. You can see that we are trying to solve the problem of heterogeneity among our data. So what it does is that what it presumes is that in the long run, the slopes of our parameters are homogeneous across sessions. Then in the short run, the slopes varies. Then in the short run, the slopes varies across sessions. So let's try to do that. Once you have that, let's type this stpmg. Then you type, we are going to find the first difference. So di, we type the short run model first. So d dot, okay, d dot, sorry, d and dot. You type d dot, then your dependent variable, which in this case is human development index. So lane HDI, then space d dot, then other variables will continue. Lane temperature, then space d dot, lane rainfall, then d dot have lane, what again? See the variables we are using in this case. Lane carbon emission. Okay, then d dot, I think this is very easy for you to memorize these ones. D dot, let's move on. Then ECG, D dot, then what again? Or the next variable. Then, okay. Remittances, then D dot. I think I use a lot of variables. I should have used just few. Then trade. Okay, then comma. Then we do for the long run. So R, then you open the brackets. Then you look for the lag and the lag in the dependent variable. So L dot lane HDI. Then after that, you write the rest of the regression. So here we are just including the ARDL model actually include the lags of the dependent variable as part of the independent variable. So that's what we're doing. We find the lag of the dependent variable, then we include it as an explanatory variable. So we've done the lag of that. Then lane temperature, lane rainfall, lane carbon. Okay. Then the next thing we do is that we have lane GDP per capita. That's economic growth there. We have lane remittances. We have lane trade. Okay, we close the brackets. Then we look out for our speed of adjustment. So the error correction model and the coefficient, that's the speed of adjustment, LE. And we'll put into brackets our Yes, LCT. Okay, replace. Then MPG. MPG. It will take some time to run. Once you've done this, it will take some time. So let's wait. So just type enter, we'll wait for it for some time to give us our estimate.
Hello, Doc.
Yeah. So
Yeah,
as we wait,
for
we can answer questions. Okay, so
So
please,
do you have
questions
any
are
questions?
welcome. Please, if you have any question, you can ask whilst we wait for the estimation. It will take some few time, so let's wait. We just have two easy. I have two easy estimation. I will just add, then we call it a day. So whilst we wait, we can, please, you can ask any question you have. If you have any challenges with the estimation, please do ask.
Okay, I think there are no questions. So, Doc,
okay. Yes.
How about the difference between dynamic regression and regression?
With the dynamic regression, what it does is that it includes the lags of the dependent variable in the model.
Okay, so the dynamic models include the lag of the dependent variable in the model. Okay, yes. Cynthia, please, you can ask your question. Unmute yourself and ask.
I dropped my question in the group chat. I was not able to pass the test PAM.
Oh, okay. What's your question?
That test PAM, I don't know. The test PAM, I'm not able to pass that stage. It's telling me not found. Really? And everything seems to be correct, yes.
Have you tried installing the test PAM? It's test PARM. Test PAM. Maybe check the spelling. Maybe it didn't add R.
Oh.
Okay, so check check the writings. It's test PARM. I'll try and share the PPT. I'll try and share the PPT I prepare on this with you guys. I'll try to do that. Okay.
Okay, Doc.
Okay, thank you.
Another thing is, I think people also have another meeting at 6, so I'm not sure if you'll be able to speed up and
okay, so okay, we have so we have to close, but we can have a look at the pool mean regression. So this is the result. The pool mean regression here. This so we have this is the long run. This is the long run result. So with the long run, the assumption here is that with the long run, the coefficient are homogeneous across sessions. It means that they are constant. They're the same across session. Then, in the short run, it varies across the cross sessions. So if you want to look at how the short run slopes actually varies across session, then what you do is that with the same model that what we tied, you just have to add full. Just have to add full at the end. And what it will do is that in the short run, it's going to show you the results in the short run, how it varies across sessions, across the cross sessions, how the parameters coefficient actually varies across sessions. That's what you will see. If you add full to your the model that we have written in the command bar, if you add that, then it is going to show you that it's going to show you how those slopes varies across session. Okay, Kwame, are you there? Hello, Kwame.
Yes, Doc, I'm here.
Any questions so far?
Yes, so
I have a problem. I have problem.
I wanted to add two questions. You know, what you have to understand, there are a lot of other panel models that you need to understand. And Actually, I didn't even touch on the one that you need to use the second generation models. That one that maybe, I don't know, maybe another time. But I wanted to suggest 2 other you can do with this once you have this kind of problem. Because the second generation model or the dynamic model, dynamic panel models, what you have to understand, and that one takes into consideration unobserved factors. Okay, what you need to understand that these fixed factor and random effect factors, they include the unobserved factors as what? As errors. So they don't make an estimation for the unobserved factors. If let's say countries are suffering from inflation, other stuff, some of these things are as a result of maybe what is happening around the world. But maybe that variable maybe might not be considered because it's unobserved. Okay, how trade between 2 countries actually influence the economic activities in the particular countries are what? Unobserved factor. So what you have to understand is that the dynamic models or the second generation models actually make an estimation for unobserved factor in their model. But with this, the fixed effect and all this, we have the feasible generalized list method. All those ones doesn't take into consideration the unobserved factor. That's what you have to take note. If there's time, then, but there's no time, I wanted to add some few ones. Just 2 of them, which would have been easier for you guys to do. Maybe I'll just type the command and send them to you. Colin.
Okay, but Doug, what I'm thinking of is, apart from the panel ARDL, you wanted to look at 2 extra models, right?
Yeah, I just wanted to do 2 estimations. Then it will be that. Yes, that's what I want to do, so that you guys will be left with the dynamic panel models. Okay, that one is more advanced. So, but at this level, you can also use those models in your work. So
okay,
that's
so
what I wanted to add. I wanted to add those few ones, then we move on.
So I think we can give you about 10 to 15 minutes so you brush on with those models.
Okay. So if you look at the result you see on your screen, this result is showing that the slopes is showing how the slopes varies across sessions, because the assumption of the panel model is that the long run coefficient are homogeneous across sessions, so they are fixed. But in the short run, what happens is that the slopes varies across sessions. So this one, country 1 will be for, let's say, you see country 1 will be for China. So this cross session. Then 2 will be, let's look at this. Let's look at our data set. You see, our data set, China is coded 1, then India is coded 2. Okay, so if you look at the result here, if you see country 2, it means that this is a long run ARDL model for India. It's showing you how the slopes varies across the sessions, the cross sessions, or the cross-sectional unit of our data set. That's what it does. And let me draw your attention also to this. With the panel ARDL model, we still maintain that your speed of adjustment, your speed of adjustment needs to be what? Negative and also significant. So if you look at this, if you look at country 1, it's what? Negative and significant. So it means that in the long run, what? The long run, there's a long run what relationship. That this change will restore to equilibrium in the long run. That's what it means. Whenever there's a disturbances in the short run, it's restored to equilibrium in the long run. That's what it means. So it has to be negative and significant. The same thing, if you look at the one that we didn't consider this, okay, see, this is the speed of adjustment. It should be negative and significant. Okay. Now let me consider, let's look at this. Let's look at where you have problem with, serial correlation and also heterogeneity. If you have this problem, you can also apply, and also you have a problem with cross-sectional dependence. Okay, you have problem with cross-sectional dependence. So if you have this problem here, you have this problem I'm highlighting, you can also use what we call the feasible generalized least square method. The feasible generalized least square method. So let me do a simple estimation. So that one, I'm just going to do the estimation, then I'll tell you what is that. So let me use that. Let me use this. Okay. I guess that's funny. I'm coming. I'm trying to hide the Zoom bar somewhere. Okay, so look at this. Let's go to, I'm just using the statistical bar there just to show you something. So you go to, wait. Okay, you go to panel. After panel, you go to, you go to contemporaneous correlation. Is it contemporaneous correlation? Yeah, that one. Then you select GLS, that one. Then here, what you need to do is that here, I will just do the estimation for just I wanted to show you, and so that I will not get back to show you again. So here, you just select your dependent variable, here. Then the variables you want to use. So the variables that you intend to use, just type them there. Okay, wait again. Okay. Let me add this. Oh, it's repeated. Okay, so these are the dependent variable. Then here, let's say you have problem, you then have to indicate the errors with your data set. So let's say in your data set you don't have serial correlation, but you have a problem with the heterostatic system. Then you select this. Or let's say you have both. There's a problem with serial correlation and also the variances is heterogeneous. Then you select this one. Okay. Then if you have problem with autocorrelation, this one is cross-section. Okay. Let's say you have problem with cross-sectional dependence. Sorry, if it's cross-sectional dependence correlated, you have to use this one. Then if you have serial correlation problems, you can choose any of this. You can choose any of them in your work. So that's what you have to do. So in our test, we have problem with this and that. So you select this. Then we can choose panel specific auto-regressive. Okay. Then we leave it as this. Here, you just have to choose the method with which you want to use to estimate. So you can just select or just leave it like this. Then, okay. Okay, so here, it means that if your model has problem with cross-sectional dependence and also there's a serial correlation, then you have to use this. Then it will be what was. Solve the problems we did here. Those problems, the estimation that we did. If you want to resolve that too, you can use what we call the panel error correction. Error correction. Okay. The panel collected standard error. Sorry, you use that one. Panel corrected standard error model. Resolve these issues here. You see the problems I told you about is this. When you have problem with multi-collinearity, auto serial correlation, and that, you just have to use any of that. So here, let's look at the other way around. Let's look at the next thing. So this one is you can use the feasible generalized least square method in resolving such a problem. That when you have such a situation, it will be able to help you to resolve that problem. Or you use the panel corrected error, standard errors. Okay, let's look at that one. Let me send this thing to the top. Okay, let me stand this. So that one is quite easy. You just type. Okay, let me show you something. You can just type this, or you can just use the same procedure I use. You go to panel data, then you go to the contemporaneous correlation and use the panel corrected standard error model. Then the same thing, you look at if you look at the errors, if your errors, your panel, your data has a problem with serial correlation, you select that. So you select any of these. Any of them is just for you. Then after that, you look at whether your panel has problem with cross-sectional dependence. If it has a problem with cross-section dependence, then you choose. So any of the errors that you have to select them here. Okay, so in our case, we have problem with cross-sectional dependence. So we have problem with also heteroscedasticity, the variance. We also have problem with that. So we select this. Then any of this is okay. We can just select any of them or this, any of them. Then we put in our values. So here, independent variable, then the variable that we want to estimate, we fix in those variables. Okay, so we're done. So once you have that, like I told you here, you have to select the variable that your data is suffering from, so that when you do the estimation, you can correct. Then, okay. So you see that, yeah. So once you do this, that error is corrected, then you can. But what you have to understand is that when you read the literature, you then have to decide whether to use the feasible least square model or use this, depending on the data, the data structure. That's what you need to understand. It depends on the data structure, then you will decide which of them that you need to use. Okay, Kwame.
Hello, Doc.
Yeah.
Okay, so
we're through here. So if at this point anybody has any question, I think the person can ask. Anybody who has a question can ask.
Okay, so we can take one or two questions and then we give you the time to rest. So family, does anyone have any questions?
If you have questions, you can ask. It's okay.
Okay, good evening, everyone.
Good evening.
Please go straight to the question so we can wrap up.
Okay, first of all, thank you for today class. I was asking about if you can give us the PPT so that we can keep on some of the points which we did not capture.
Oh, okay.
Yeah.
I'll try and give you that. That's my personal property, but I will share it. No problem.
Okay, so we will take the PPT from last week and this week, and also maybe the do file for today's
which
lesson.
one?
The PPT.
Okay, that's the time series one. The time series one. Yeah, okay.
And then the panel data. And Doc, thank you so much. Thank you so much. At least we've learned about
also the PDF.
5 models.
The PDF is also required.
I think with the
the PDF. Yeah.
Oh, okay. Okay, no.
You can claim the do file.
No, I'll give you the PDF. Don't worry. The way in the course of it we had a break and I have to open the newspaper. But don't worry, I'll get you the PDF.
Okay.
Okay.
I'll get you the PDF. I'll send that with my own personal property, the PPT. I'll send that. Anyway, thank you all for taking time to attend this class. I hope I'm able to impact in some way. Okay.
Okay. Thank you so much, Doctor. Indeed, you've really impacted us and we appreciate the time. So we will excuse Doctor so he can have a quick rest and maybe have dinner as well. So, Doctor, thank you so much, and do have a blessed evening.
Okay.
We will get in touch as well. And I'll share your WeChat with the group for people to come back to.
Okay, no problem. Okay.
Okay,
All
thank
right.
you so much, everyone. Okay, so colleagues here, one thing I can say is we invite all the African students here to join OAAD, which is an association for African academic doctors. We try to impact each other. We try to embark on things that are feasible, practical, so that we will empower ourselves for the benefit of the continent we are coming from. So if you are an African student here pursuing doctorate degree and you are not in any of the group, I kindly ask you to get in touch with Odi in the WeChat group or Huda so you can join the group. It's a blessing to have all of you here, and what I can say is let's keep practicing. Please don't go through the video in one sitting. Take it one at a time. Take it one at a time. You can start with how to handle panel data. You tackle the fixed effect, random effect, and then the pooled. Then you go through the process of deciding between whether you should use pooled or random effect or fixed effect. From then, you can then go into whether you want to do the pool mean regression, which is the panel ARDL, or you go into cross-sectional dependency, and then you can go into the other two models as well. This is PowerPad, and I wouldn't lie to you, it will take time, even if you are reading the literature by yourself, to get them. So with this as an introduction to them, you are really, really equipped. And I am hoping that they will come in hand when we are writing our thesis, our papers, and all that. I know you are tired, so we wouldn't have a Q&A session. But if you have any question, please feel free to ask. When you ask in the group, we will definitely respond to it. Or you can also contact Doctor and then you ask the questions. So with this said, thank you for having you around. If you have a question, you can ask. If not, we'll call it a day. In Vietnamese, can I join? For the OAAD group, it's purely for the African students pursuing doctorate degree, whether in China or whatever country. So for that one, I don't have control over it. But whenever there is a program, you are free to join anytime. And as I said, there is a plan for data analysis with R. There is a plan to have one for Python. And also there is a plan to have more of such programs. So whenever it comes around, we will be publicizing it for you to join. So thank you so much for having me around. If no other question, I think we can call it a day. So hello, people.
Thank you, guys.
Okay, thank you so much. And we'll post the whole the project work. Please
Thank you, brother
complete them for us.
Thank you.
One thing I have to say is that those who applied for the certificate, we'll publish the final list online and you can audit it. If you still need a certificate, you let us know. If you no longer need it, you let us know so we can clean the data up. We don't want to make the certificate for people who no longer need it. So if you need it, please check the list again, confirm if your name is correct, and then we can print the certificate or email it to you. Thank you and have a good evening. It's Halloween. Let's go and scare people. Bye.
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 Have a nice evening too.
Bye.
Focus on the also it's about annual income of the person with doctor for the focus on topic announcement and October. Original time is analysis and perception of what is called a relational graph. Talking about design and conceptual relationship. Then we will have all the online.
Okay, so people, respectfully, we are going to end the meeting so we can all have a rest. So thank you so much and have a blessed evening and weekend. Okay, meeting is over. So